Wonderful. Am I coming through there? Very good. So it's my honor to introduce Professor Nanshu Lu, who is an associate professor at the University of Texas at Austin in both aerospace engineering and engineering mechanics and in biomedical engineering. And in her talk, you're going to see how those two pieces fit together. She's been at Austin since 2011 and was tenured and promoted associate professor in 2017. She's won a large number of honors, including the Technology Review 35 under 35 and NSF, AFOSR, ONR, and 3M Young Investigator Awards. She received her PhD at Harvard and then was a Beckman Fellow at the University of Illinois, Urbana-Champaign. And her laboratory's goal is to capture the information that our bodies radiate in using flexible, stretchable, and biointegrated electronics, such as in electronic tattoos and implantable devices. So Professor Lu, welcome. We're delighted to have you as one of our rising stars. We're looking forward to your talk, your perspective, and your wisdom. Thank you.
Thanks a lot, Paul, for the kind introduction. Hello, everyone. This is Nanshu from UT Austin. I'm currently in my home at Austin. And I would like to express my gratitude and delightness to join so many superstars and rising stars on iCANX-Talk platforms, which is now becoming probably one of the most influential online tech and scientific webinar platforms. Thanks to, of course, Professor Alice Zhang's personal charm and energy and dedication. And I am also extremely honored and delighted because today I am honored by ACS Nano, as well as our two nano heroes, Professor Paul Weiss and Professor Yuri Gogolty. This is going to be a very memorable moment. So I am happy to share with you our latest development for multimodal electronic tattoos. So why we are interested in this area is actually because nowadays we see a huge trend to mimic, for humans to mimic robots and for robots to mimic humans. And as well put by Elon Musk, he said that humans must merge with machines or become irrelevant in AI age. And this kind of vision for merging humans with machines and electronics is shared by already many iCANX speakers. If you followed iCANX talks, including Professor John Rogers, Professor Zhigang Suo, Xuanhe Zhao, Cun Jiangyu, Bing He, and many speakers to come. So the ultimate goal, of course, is to be able to have a seamless interface between the two. However, if we look at the reality, we can see that currently on this well-designed industrial machine, such as a car, there are more than thousands of sensors. But on our human body, we rarely have any reliable long-term unobstructive sensors. But we can think both of them as machines. Human body is just a soft machine, right? So both of the machines are radiating data about their health, readiness, and specific to human body, our emotion and intention. There are multimodal data radiated from our body, including physical data like temperature, electrophysiology, and mechanical data as well as mechanical data like blood pressure, motion, and even including chemical data such as our sweat analytes. So currently, however, we are not very well digitizing our human body. So what are the opticals here? We can see that conventional, there are already a lot of conventional wearable devices trying to digitize our body for different purposes, such as mobile health, performance monitoring, human-machine interaction, and so on. But currently, we see those as bricks and straps because they are based on rigid wafer-based electronics and they are intrinsically bulky and obstructive. On the other hand, our vision, actually first proposed by Professor John Rogers, is to, whether we can make those wearable electronics as thin, as soft as our skin, such that we can patch them like a temporary tattoo sticker. Of course, to achieve this vision, there are many challenges from the mechanical mismatch to low-cost, high-yield manufacturing to long-term wearability and biocompatibility to power data handling, as well as how do we really provide value to our users. So therefore, in my group, we continue this vision to ultimately achieve those kind of soft bioelectronic systems that are really practical for human body digitization as well as therapeutics. So to achieve this goal, we have to perform fundamental research, and my group is focusing on the following 4 thrusts. One is the mechanics of flexible and stretchable structures. This is a continuation from my PhD work, and we are currently looking into the mechanics of the passive and piezoelectric serpentine ribbons. Those are stretchable and soft, no matter what is the material. And we are also looking at the bending of multi-layers with huge elastic mismatch. And we have discovered that the conventional Euler-Bernoulli beam theory of the linear distribution of the strain in the thickness direction completely breaks down, and we have found the split of neutral axis in those stiff layers because the middle soft layer can endure enormous shear and decouple the 2 layers. Today, I'm not going to talk too much about this, but it is really driven by mechanics findings. And the second area is the manufacture and the transfer of those soft stretchable electronics. And we're going to focus on the cut and paste and later the cut solder paste process for the free-form digital manufacturing of those stretchable electronics without using any MEMS technology. And we are also collaborating with other groups to study those water-assisted transfer printing process. After we manufacture, we design and manufacture a good device. It doesn't mean it can always be successful and high fidelity because integrating electronics with bio tissue is very tricky. One, because the interface may not have those most intimate connection. We are looking into the bioelectronics interface, mostly mechanical interaction between them, because the mechanical interaction is going to dictate the thermal, electrical, optical interactions. And we also try to engineer a more robust and reversible interface adhesion as those inspired by octopus crater arrays. And we have done a lot of mechanic studies for different factors in the system. And this work was completed by a previous PhD student, Dr. Liu Wang. Now he is looking at wet adhesion with Professor Xuanhe Zhao at MIT as a postdoc. So ultimately, we also want to incorporate emerging nanomaterials such as 2D materials and recently also carbon nanotubes to make those electronic tattoo devices for their thickness and intrinsic mechanical robustness and advanced electronic and optical properties. I'm going to share a little bit about those graphene electronic tattoos. We call them GETs. And from our fabrication, we also noticed a lot of interesting defects when we transfer 2D materials onto various surfaces. For example, a lot of micro tints or micro bubbles. And we studied their intrinsic mechanics governed by the interface properties and the intrinsic material properties of the 2D materials. And this series of work is completed by a fresh PhD graduate from my group, Dr. Zhao Dai, and he is going to become a Marie Curie postdoc fellow at Oxford University this fall. So unfortunately, I'm not going to be able to cover too much of those details today because I'm going to focus on the mechanics and manufacture of those electronic tattoo systems today. So if we look at the mechanical property contrast between silicon and skin, we can see that silicon wafer is intrinsically rigid and brittle, whereas our human skin is intrinsically soft, curvilinear, and dynamic. Their Young's modulus mismatch can be as high as 6 orders, and our skin does not rupture until 50–60% strain, but when I stretch our skin by 20%, we start to feel pain. So I call this 20% to be the ouch limit. It's still 20 times difference. So to overcome this kind of huge mechanical mismatch, there are many researchers focusing on developing intrinsically soft organic electronics represented by Professor Zhenan Bao and Takao Someya and many young professors like Professor Cun Jiangyu and so on. So, but for our mechanics people, we adopt a purely mechanics approach, which is by changing the geometry of inorganic electronic materials like metal, silicon, 2D materials. So we know that by mimicking a 3-dimensional spring, a 2-dimensional meandering shape, which we call serpentine ribbons, can still stretch and uncoil and to achieve high stretchability and high compliance, essentially out of any materials. And we can see when we stretch this by more than 100%, the intrinsic strain inside is less than 2%. We have done a lot of theoretical and numerical modeling for this serpentine design to really minimize their stiffness and maximize their stretchability. We also looked into their softness, as you can see here, comparing a linear ribbon with a serpentine ribbon of the same material. We can see that their stiffness can be reduced by orders of magnitude, even if we just change their geometry. We're not changing their electronic property, optical property, or anything. It's purely a geometric shape change. And this kind of orders of magnitude reduction in stiffness gives us the hope to build really skin soft tissue-like electronics out of intrinsically stiff materials. So of course, the epidermal electronics is a very exciting representation of such design. And we were able to design a two-dimensional filamentary serpentine network, which is able to demonstrate a mechanical even smaller than a pig skin. And Professor Yihui Zhang also developed a variety of those serpentine patterns such that he can clearly mimic this whole stress strain curve for skins. And because of the thickness and softness of this now we call them electronic tattoos for human to wear. So those e-tattoos can be placed on any part of the skin, for example, around human neck, where it's very easy to deform and very easy to wrinkle. We are able to measure the neck electromyogram when we speak different words. And by pattern recognition, we are able to recognize what you are trying to say, not through your voice, but through your neck muscle activity. And we're able to build a human-machine interaction game based on neck EMG. At that time, the fabrication of the electronic tattoo was using MEMS like fabrication in the clean room. So as you can see, it includes the transfer printing of silicon nanomembranes, metallization, and patterning of the circuits and building the devices layer by layer. This is a highly simplified schematic. So the whole process is based on photolithographic wet process and rigid wafer for handling purpose. And as you can imagine, it's very time consuming and very costly. So at UT Austin, we are trying to look at freeform manufacturing or digital manufacturing. Freeform means we don't want to use any mask or stencil. The first thing comes to mind is printed electronics, which is additive manufacturing, but there are many limitations, such as the time taken for ink annealing, and even after annealing, the ink still has much higher resistivity compared with the metal. So they, when they are made as antenna, they can be lossy. And the silver or copper inks are easy to oxidize and react with sweat. Gold inks are way too expensive for disposable electronic tattoo use. So therefore, we start to look into subtractive manufacturing, which is actually consistent with the conventional PCB manufacturing process. We use mechanical or laser cutter plotter to selectively remove the region. And we are able to use this process to process already sheet-like thin films such as copper, gold, graphene, or even piezoelectric materials. And it is also completely dry process. So at first, we started with a very economic desktop mechanical cutter plotter, which is designed for paper vinyl cuts. And at the tip of this cutting head, there is a little blade that is able to move according to the imported design patterns. And we immediately try to cut, for example, aluminum foils. But actually from my PhD study, I know that those thin film, freestanding metal thin films are not very stretchable because all the large deformation are focused at this single neck. So the global stretchability is very limited. However, if you support the metal thin film by a strong and well-adhered polymer substrate, you are able to achieve more than 50% stretchability without any fracture, without serpentine design. So it's intrinsically very robust. And the best example of contrast I can give you is aluminum foil freestanding metal versus this kind of potato chip bag, which is polymer laminated aluminum. You can have a very intuitive sense which one is more stretchable. And also, fortunately, on the market, you can find those metallized polymer as big rolls. They are developed for RF shielding or thermal reflection purposes. So we can directly buy those big rolls of gold on PET or copper on Captone, or you can customize from the vendor. And you laminate this metal polymerized metal sheet on a temporary support, such as a thermal release tape. And you put into the cutter plotter, either mechanical or laser, and you can form those cutting seams, and then just by heating the thermal release tape, we're able to deactivate the adhesive and remove the extras. And then the leftover circuit can be easily pasted onto a target substrate, which could be a medical tape or a tattoo paper or directly on our skin. The whole process only took us 10 minutes, and it is completely free-form and dry process, as you can see. You can repeat this process multiple times to cut and paste multiple materials and multiple devices onto the same substrate. And you can directly solder microchips, as I will show you later. It has almost unlimited size because we're not using any rigid wafer. And it is also compatible with roll-to-roll process in the future. So this was our first cut and pasted electronic tattoo. My first PhD student was twisting my arm, and he is now actually working at Google. And he is able to show those mechanical reliability for serpentine coils, as serpentine ribbons, as well as straight ribbons have very different stretchability. And even after 10,000 cycles for those serpentine ribbons, there is limited change in resistance. Before and after skin deformation, there is also almost no change in resistance. So even just using this kind of very simple passive electronic tattoo, we are able to achieve quite a few electrophysiological as well as thermal and mechanical sensing, as you can see. The key is to patch the e-tattoo at the right location to measure the right thing. On the chest, we measure ECG. On any muscle, we measure EMG. On the brain, we measure EEG. And on any part of the skin, we can measure skin temperature, skin hydration, and by integrating electrically conductive rubber, we can measure the skin deformation using those as soft strain gauges. So the intrinsic merit of electronic tattoos compared with conventional rigid electronics lies in their coupling with our skin. Under optical microscope, our skin is rough, and this is not our work. This is from Professor Rogers' work. So we can see that only when the device is thin and soft enough, it is able to conform to the finest wrinkles of human skin versus conventional rigid devices are sitting on our skin like a rigid board with very limited contact area. That is going to limit the interface impedance to be a high level, and that can lead to very low signal to noise ratio. And also when we have this kind of integration, we are able to limit the interface relative motion even when the skin is under large deformation, and that can minimize a lot of motion artifacts, and it can also enhance the interface thermal or mass transfer. So we actually performed a lot of analytical modeling to review how thin and how soft you need the e-tattoo to achieve 100% conformability. That is one. So as we can see, our prediction for EcoFlex on skin, only when it's thinner than 7 micron, it is able to achieve 100% conformability, and that is fully consistent with the experimental findings. And also interestingly, once we exceed 7 micron thickness of the ecoflex, it's going to drop the conformability in, significantly all of a sudden from 100% to 24%. That is a snap-through instability in mechanics. And then at 36 micron thickness, almost no conformability, almost no conformability here. 100 micron, forget about it. So therefore, actually, a visiting student, Youhua Wang from Huazhong University, is the HUST is able to demonstrate this kind of limited motion artifacts in ultra-thin e-tattoos. So this is Youhua's picture. And we are able to show, even comparing with wet gel electrodes, which is the gold standards, the ultra-thin e-tattoo is able to show immunity from the motion artifacts. The slightly thicker dry e-tattoo has motion artifacts similar to the gel electrodes. So this shows the importance of the thickness and softness of the e-tattoos. So also in Youhua's paper, he was able to demonstrate the synchronous measurement of multimodal physiological signals such as skin temperature, skin hydration, ECG, using one piece of multimodal e-tattoo. As you can see at that time, we still use gold connectors to connect to this e-tattoo. And we were heating up the subject. We can see the temperature rising lead to also sweating. And when it's full of sweat, however, on the interface, we still measure very reliable ECG signals, as you can see in the blown up view here. And the sweating is not affecting the performance of the e-tattoo. So after Youhua returned to Huazhong Keda, he also engineered this very large area, multi-channel e-tattoos for electrography at scale. And he was able to put this large area multi-channel e-tattoo on human arm, on human chest, for multi-channel ECG or other locations that has highly curvilinear surfaces. He developed a very innovative transfer printing process, and he was also able to compensate for the noises coming from those long interconnects. That is a real challenge for large area sensing. So hopefully our paper can show you more details as it comes out. And he was able to train a machine learning algorithm such that the algorithm can recognize our 26 alphabet sign language through this kind of 16-channel ARM EMG. And of course, we can control processes and many other things as a reliable human-machine interface. So when we have those kind of mechanical motion for EMG, we also confirmed that under long term, up to 6 hours, and under a variety of motion, we are able to maintain the high signal to noise ratio for e-tattoos compared with conventional rigid box DALSYS EMG systems. And this is, again, thanks to this robust interface between the two. So therefore, because the bioelectronics interface is so important, and we are not really trying to increase the interface adhesion too much, therefore, our goal becomes looking for the thinnest material to have the best conformability. And of course, the world's thinnest material is 2D materials, and we are able to build a graphene-based electronic tattoo, which has combined thickness and stretchability. Comparing with other materials like hydrogels and liquid metal, they are very stretchable, but usually the devices made out of them have a certain thickness. And in the middle is a lot of nanocomposites, and those are 2D materials conventionally not too stretchable. And later, Professor Takao Somaya engineered those gold nanomeshes, also very stretchable and ultra thin. So the way we manufacture those graphene e-tattoos are still using the cut and paste dry patterning process, but we have to do wet transfer for those CVD grown monolayer graphene on copper using a PMMA using a PMMA permanent support. We never dissolve away PMMA. And when we pick up the graphene PMMA bilayer, we make sure graphene is facing up. So after this wet transfer, there's no more wet process. Therefore, the graphene surface is kept very pristine and very clean. And because the graphene e-tattoo is only 300 to 500 nanometer thick, dictated by PMMA thickness, we can easily transfer onto human skin without any adhesive. And we, of course, care a lot about the mechanical reliability of GETs. So we tested the stretchability of a straight GET specimen without serpentine. This stretchability actually really surprised us, because we can see that compared with the 100 nanometer gold on 300 nanometer PMMA, monolayer graphene on the same substrate has much better stretchability, and gold just behave like a brittle material, rupture at 1%. So this kind of large stretchability, however, does not mean graphene did not rupture. So when we look into the resistance and the slope of the resistance curve, we actually, with in situ observation of the microstructure, we actually observed 4 different regimes of the deformation. In regime 1, that is between 0 to 0.9%, we saw a lot of we didn't see any microcrack. There are occasionally defects in the CVD graphene, and but starting from 0.9%, we start to see very micro length cracks emerging in the monolayer graphene. But those cracks grow to a few micrometers, and then they start to populate. They don't really propagate that long, but they become more. So that is from 2.5 to 8%, and eventually they start to grow, and also the PMMA support start to have macro cracks, and those macro cracks eventually kill the whole stretchability. So ultimately it fails at 18% completely. So this means we still have crack starting from 0.9%, and therefore the resistance will have a high hysteresis. And we are going to study more about the cyclability and improvement of the fatigue behavior of those kind of GETs specimens. So here is a video showing the direct transfer printing of GETs directly on human skin by smearing some water on the temporary tattoo paper. There is a water-soluble adhesive on the other side, and we can directly transfer GETs simply like a temporary tattoo. This work is actually published on ACS Nano very efficiently. So under optical microscope, you can see this transparency and the conformability of those GETs. Because of those transparency, when we even wear the GETs on human skin, you are not able to tell, and you're not going to scare away your friends. So here on human face, we have those electro-oculogram sensors around human eyes, but you cannot really tell. And we can use those EOG sensors to very accurately control the motion of a drone following our eyeball rotation. When we look up, the drone fly up. When we look down, the drone fly down. And from the front, there's no camera on the drone or anything. If I didn't tell you, you couldn't really figure out how we are really doing that. So we call this imperceptible human-robot interface. So moving on to really value proposition, we want to look into significant unmet medical needs, and we identified hypertension and continuous blood pressure monitoring to be one of the most significant unmet needs. It is currently the silent killer for a lot of especially elderly patients. And currently there's no way for continuous blood pressure monitoring except you use this invasive arterial line, which is inserted into your artery to perform continuous blood pressure monitoring. This is the gold standard, but it's only used mostly in ICU patients. So we actually proposed a indirect way to extract blood pressure using the cardiac time interval for heart. So here we developed, we try to look into the mechanical signal of our chest due to heartbeat, which is called a seismic cartogram. And we can see at every heartbeat, there are two sounds or two vibration peaks. And only in this middle locations, through this digital image correlation study, we found that only at this middle location, we're able to measure both very clearly. So we built a dual mode ETA2 that can synchronously measure ECG and SCG. And the SCG peaks identified our mitral valve closing, aortic valve opening, those kind of cardiac events. And by combining the two of them, we are able to extract all the cardiac time intervals, such as the systole, diastole, pre-ejection period, and so on and so forth. So the systole represents how fast our heart contracts in every heartbeat. And the faster one's heart contracts, which means the smaller RAC interval, that gives us the higher blood pressure value. So this is a empirical calibration curve to identify this kind of correlation between systole and blood pressure. And using this kind of calibration and using this kind of continuous systole measurement for every heartbeat, we're able to extract the blood pressure continuously, even when we have a very abrupt blood pressure change, when we, for example, internally pressurize ourselves. And it compared very favorably with a continuous and non-invasive blood pressure sensing system in the market, which is based on pulse transit time estimation. So as you can see, we still use the wires here. So to go wireless, we need to leverage existing wireless technologies such as near-field communication or Bluetooth. So they have their own pros and cons. Near-field communication is designed for one-time reading, like our access card, but they have very low power. And the Bluetooth transmission can be long range, but they have very high power consumption. So to integrate those kinds of IC chips onto our cut and paste ETA2, we developed cut solder paste process where we still perform the cutting to define the circuits, the interconnects, and the antenna, but we transfer the patterned circuit onto a water-soluble tape supported by a Kapton support, such that we can do direct soldering onto the circuit. And because Kapton has very high thermal budget, and therefore we can do the pasting and then water soluble tape dissolving, and at the end we can end up with a active ETA2 with those integrated circuits. And we can, of course, stack up multiple layers of this active circuit to form a completely wireless ETA2 with a disposable electrode layer, readout circuit layer, and NFC layer, for example. And they are designed into this modular concept such that our wireless layer is very generic. Doesn't matter what you are trying to measure. The readout circuit layer is customized for different signal acquisition. So for ECG, hydration, and blood oxygen saturation, you can see the designs are different. But then those are different layers that you can easily pick and customize depending on your use. This is the merged view. So here we demonstrate their sensing capabilities for ECG, oxygen saturation. Here we are still using fingers, but it is possible to directly measure on the chest or on the neck. And temperature and hydration, as you can see, we actually have to use a near field reader to both power and read from the ETA2 because the ETA2 is battery free. And even though we integrated those rigid IC chips, because of the mechanical optimization, they are still very robust and such as bendable, stretchable, twistable, and waterproof. So when cell phone NFC-enabled cell phone approaching the ETA2, we can start all the reading. So this kind of multi-layer and modular design has a very cute benefit, which is that after the measurement, we can peel off the ETA2 from our skin and then disassemble those different layers. We can disassemble and assemble up to 20 times, and we can still continue to use this ETA2. So the only caveat is that we want to dispose the bottom layer, that is the passive electrode layer. This passive electrode layer is very low cost and not very troublesome to dispose. So ultimately, we want to have a Bluetooth long range communication. Therefore, we need to integrate a battery. But the battery is a very small coin cell battery, so we still need to have a wireless charging capability, not by taking off the ETA2, but while the ETA2 is still working. So I'll demonstrate to you how. And here we are showing you the Bluetooth-enabled wireless ETA2 simultaneously measuring a single-channel electrocardiogram and single-channel seismocardiogram, and 3 axes of our body motion. And you can see that when the subject was static, there is a very clear signal, but when he started moving, the ECG looked fine, but the SCG is very sensitive to those motion noises. To achieve a charging on the go purpose, we have to design a strategy that the cell phone can stay in our pocket instead of held in front of our chest. So we use this kind of fabric feeding coil, which is a piece of soft fabric with a conductive silver coil sewed on them. So the idea is to repeat the electromagnetic field from the cell phone, which is safely placed in our pocket, to the ETA2, which is beneath the shirt here. And we can see that in this case, we are able to have a 2-stage charging mechanism, which has an efficiency about 50% of the 1-stage charging, where your cell phone is directly facing the ETA2. So this charging on the go strategy is able to extend the wireless operation of our ETA2 to be almost unlimited, just limited by our cell phone, versus without charging, the coin cell can only work for a few tens of minutes. So in summary, I have demonstrated to you some fabrication and application of ETA2s at different body locations. And there are many other cases that I'm not able to show today, but I just want to emphasize that this is a really robust and versatile platform that can be put at different locations to measure different things. In terms of functionality of sensing capabilities, we can sense all those physical signals as well as chemical signals, where you will hear from Professor Wei Gao in a minute, and he can give you a very fantastic view for this part. And ultimately, if we can have a sensor network, we hope to be able to do data fusion to look at not well-defined things such as stress, fatigue, or even COVID-19, as Professor Rogers mentioned in his EML seminar. And currently, we know that in the US, there is a thermistor company called Kinza, and they collected their smart thermistors, which digitize and upload users' temperature. And they have a big data platform that saw the temperature rise of the population back in February. And they are able to predict the outbreak of COVID-19 in the US. So this kind of wearables would able to provide those aggregated data to look at even population health and pandemic forecast. So with that being said, I also want to emphasize that because we can form such an intimate bioelectronics interface, we can also achieve those kind of electrical stimulation. Here we are trying to use electrotactile stimulation to give sensation to our skin. If it's too weak, you feel nothing. If it's too strong, you feel pain because you are shocked. So at the right combination of voltage and frequency, we'll feel the sensation, and we are able to deliver communication to the skin or mechanical feedback to the skin. So that is only one example. There are many examples that I'm not able to cover today, but I borrowed this picture from Professor Daehyun Kim's paper, and I modified a little bit to try to really show you a vision for future bioelectronics. No matter invasive or non-invasive, we need to have those sensing capability and hopefully data processing and analysis capability either on the tattoo or in the cloud, and then provide those information to medical care providers to come up with diagnosis and treatment plans, and eventually deliver those treatment or therapeutics also using the e-tattoos. Of course, energy and the power supply is a big bottleneck currently, and as you heard from Miso, there are many efforts in this area already. So looking forward, I see this area to have a lot of future opportunities in different disciplines. We need continuous innovation for new materials, electronic circuit design, especially ultra low power integrated circuits, the mechanics for the integration and interface, bioelectronics interface, and different manufacturing methods for those kind of especially long-term high-fidelity wearable sensor network. The data handling is another very active area by data scientists, because now we can provide them with so much new data. And it's important to really have a passive operation for our users, because they are not able to spare attention to any wearables. And ultimately, our ultimate goal is to really close the loop of sensing, maybe edge computing or cloud computing, diagnosis, and therapeutics, all on the wearable e-tattoo. Of course, there are many challenges ahead because of the lack of ground truth. Outside of clinical settings, we have to do tons of experiment to establish those ground truths, and we have to identify those digital biomarkers clearly, especially for things like stress, depression. Those are not very well defined. And the quality of data, especially due to motion artifacts and environmental effects, and sweating infections and so on are still a big issue. And we, of course, care about our users' safety and privacy. And we also need the buy-in from all the stakeholders, such as patients, doctors, insurance companies, regulatory agencies. And after you consider all of those stakeholders, you realize that maybe at the end, technology is a very small piece, but it is the fundamental enabling tool to make all this happen. With that, let me acknowledge my group at UT. We went for a speeding car, racing car competition. And Hyo Yang is the one who developed the wireless e-tattoo, and he won the championship with his girlfriend. And he is now a postdoc with Professor John Rogers. And we are very grateful for our financial sponsors, and a special thanks for Alice of organizing this global tech webinar, which is able to really share the best and foremost of our science advances. And again, special thanks for Paul and Yuri's dedication for this platform and for the big honor. And finally, I want to thank you all for your attention. Thank you.
Okay, great. We came to the question part.
Terrific, thank you. I think that was just a tour de force in what one can do, and especially in setting up a new lab in such a short time. I can see that Alice has the question on her
It is
page.
on.
Hoping it moves over to Baidu. There we go. So the first question is for the laser subtractive technology, in addition to increasing the accuracy and reliability of the equipment itself, how does one increase the consistency of processing through other means, such as materials selection or graphic design? That's interesting. Yeah.
Yes, that is actually a great question, because currently we are able to use the laser processing for not just the monolayer or freestanding material, but also multi-layer materials. So for example, I mentioned that we should use polymerized metal thin films instead of freestanding metal foils. That that comes from a mechanics consideration. And for 2D materials, we are not directly processing monolayer graphene, but we're processing PMMA supported graphene, and we're able to see the effect of PMMA in terms of the mechanical reliability of those graphene electronic tattoos. So those are two examples I gave. And in the future, when you want to design this kind of optimized manufacturing process, you have to consider not only the material property, for example, the laser material interaction, but also the mechanical property of your ultimate device. By layering materials, or by even 3D design of the lattice structures, for example, like Miso mentioned. The laser is very powerful, and the resolution and cutting quality is requiring a lot of optimization.
Good.
Terrific. Next question. I have a delay while it comes up on Baidu. There we go. No, that's the same one.
Paul, can you see that?
Yeah, I can't see it in Zoom, only in Baidu. There we go. Professor Lu, very nice talk. For the electronic tattoos, is it always one layer? Can it be multiple layers? I think you already answered that. And if it's multiple layers, how do you get alignment?
Yeah, thank you. I didn't really talk details about alignment because currently it's manually aligned. I guess the audience is asking about our multi-layer modular design at the end. So in that case, first we engineered VS between each layer, and we are able to use actually our long form pattern, not just for advertisement for UT, but also as alignment markers between the layers. So in the future, of course, there are a lot of digital alignment technologies that we can leverage if we want to automate the multi-layer lamination process.
Very good. And actually, while the next one comes up on Baidu, let me ask you, how reproducible are the signals and the devices that you make, and how difficult is it to associate those signals with biomarkers that, for instance, a clinician might want to have or use?
Okay.
It's not the question on the screen. We'll come back to that one in a minute. So I slipped in a question.
Which one?
I slipped in my own question. Sorry, Alice.
Okay, I see. Okay.
Thanks, Paul. Can you speak that again?
Yes, the question is, how reproducible from one to the next are the devices and the signals, and how difficult is it to associate these new, signals that you record with biomarkers that are known, for instance, by clinicians?
Right. So the repeatability is varying a lot depending on the type of the signals we're acquiring. For the electrophysiological signals, those are the most repeatable, and they have a very standard, very nice established gold standards, and we have to perform all those correlation analysis and statistical analysis to confirm, or we call it the non-inferiority tests of our wearables. For other signals such as the mechanical signal, the chemical signal, those are really emerging signals which don't have much gold standards. For example, for our seismocardiogram, we were using the digital image correlation. There are also stethoscopes out there to listen to the heart, which is also acoustic mechanical signal of the heart induced chest vibration. In those cases, they are not exactly the same signals. So there are a lot of work to be done to establish those ground truths.
Terrific. And then the next question from our audience, Dr. Lu, amazing technology. How about the power issue of these multifunctional electronic tattoos, including what is the power consumption and how do you supply power?
Right. So currently we are using the Bluetooth wireless transmission technology. It's the standard Bluetooth low energy technology with power consumption of a few milliwatts. So currently we are able to use the near field communication, also commercially available NFC technology to deliver this kind of a few milliwatts of power. And we showed that we can use a fabric feeding coil to achieve the charging on the go objective, such that we don't have to take off the e-tattoo to place it on the charger and then replace it on the skin. So by using this charging on the go strategy, we hope to achieve long-term continuous monitoring ultimately, for example, 3 days or 7 days. That would provide a lot of valuable data to also study the circadian rhythm or sleep disorders or many other human performance tracking kind of purposes.
Fantastic. Let's see, the next one is just coming up. Give me 1 second while it appears in the other format.
Okay, did you get it?
There's just a delay getting over to Baidu.
Okay, yeah.
There we go. Do you think about using this technology to help traditional Chinese doctors pick up biosignals to presumably detect their effect and follow their course of action?
Yeah, this is a really emerging field. We have not done much in this field, but for example, Professor Xue Feng in Tsinghua University has published papers about highly sensitive pressure sensors that can measure the full pulse wave on the wrist. And that is actually a traditional Chinese medicine method to tell the health of a subject by using our fingers to feel the pulse waves. That's how we conventionally do it, but it is totally possible to digitize the pulse wave and analyze the patterns to really give all the doctors information about the pulse waves, not just highly experienced and doctors with highly sensitive fingers. So that is just one example. There are many possibilities. Yes.
Very good. I think we're going to have to move to the panel rather than continuing with the questions, but we will forward questions to you and the other speakers. We thought we would impose upon all three of our rising stars to talk a little bit about their careers and about how you developed your research program, and also about how in the current situation you're able to work with your group and to reach out through the world. Before that, I want to present you with this certificate, thanking you for being one of our Rising Star lecturers in advance for the piece that you'll be writing for us, and also for your advice for the journal and helping guide not only the future of the journal, but the future of our field. Congratulations on everything you've done and on this particular recognition of it as well. Thank you.
Okay, as Paul said, we move to the dialogue part for the ACS Nano Rising Stars. Okay, I'm coming. So, yeah, Miso, Nanshu, Wei, Yuri, Paul, please, yeah, turn on your camera. Yeah, we got here. Okay, Paul, it's really excellent. Thank you very much for having all these rising stars getting on the stage. I think I'm really proud of them. Like just our Miso and Nanshu really deliver wonderful talks. You already come out the questions what we want to talk in this dialogue part. I want to get all the young stars to say something about your group. Yeah, like this. Okay, Paul, please. Yeah.
Yes, maybe let's start each with how did you choose the problems to address when you started your research groups, and how do you choose to evolve those as you go forward? Maybe let's start first with Nanshu. We have you up, and then we'll go to Miso, and then we'll go to Wei.
Okay.
Sure. Thank you. So first of all, I'm very flattered to be still called young stars because I am much more senior than Miso and Wei, but I am really honored to be still considered as rising. So that's very encouraging. And I have 3 points to make for developing an academic career. So first, I think that's very important, like Paul said, how do we pick a topic for our independent research? And my perspective is that we need to have a vision that is decades in the future, looking forward into decades in the future. And we have to do everything possible to make it come true. Maybe not within 2 or 5 years, but ultimately it is our vision and it is our responsibility to make it come true. And I'm a fan of Elon Musk, as you can see, and because I really appreciate his vision. So we say he is the lost child from Mars, and he's doing everything he can to return to Mars. And his goal is to achieve interstellar transportation. And to do that, he needs recyclable rockets to reduce the cost. He needs energy storage, such as lithium-ion battery. So he created Tesla. And he needs transportation on the planets. So he has the Boring Company for the Superloop transportation. And he needs collaboration between human and machine. So he has Neuralink to establish that interface. So I think we can learn a lot from, and I don't know when we can achieve interstellar transportation, but that is how powerful a vision could be. And my second point is that if we want to achieve this vision, we have to learn, have lifelong learning from everybody we can encounter, from our colleagues, collaborators, and even our students in the day-to-day basis. And we just cannot be satisfied with what we have learned in PhD or postdoc. We have to keep expanding our domain technology, and because we have to do everything possible to realize our vision. And the last point is that we also don't need to be shy to ask for help whenever we need it. Sometimes we are afraid of bothering or wasting colleagues or mentors' time. But I think the best way for us to pay back is actually to pass this tradition of helping junior colleagues and scientists in the community in the future by helping the scientists junior to us. That is a way to pay back to the community, because they are carrying this tradition so well, and we should do the same thing. Thank you.
Super. Yeah.
Thank
so,
you.
Maisel?
I think Nanshu gives me some challenges because she mentioned everything great already, and then that I have to say, I guess. So I have to add, I want to add one more thing about that. So when I chose the topics of metamaterials, or before that, energy harvesting, the reason why was, it might be a cliche, but the reason why I chose those topics is because I love them. I didn't know why, but it didn't go away. So I have so many opportunities to see many topics, research topics, like from conferences and everywhere. But sometimes some specific topics didn't go away from your mind. And if it lingers, you can start studying. And then if it still stays there, then you need to jump in. And that gives you some other way, and that shows you the way to go through. And that's how I stepped up, and up to now. And these days I have another keyword that I have in mind, and that's lingering. So hopefully I can make some different build out with those keywords. But like I'm not talking about just the instinct. So once you love it, you have to study, even though it gives you some hard time to understand. Because for me, metamaterials, the physics and mathematics, it was so challenging to understand in the beginning. So there's a really big like activation barrier to jump over. But now I think I'm getting used to it, and I feel more interested in that topic, and I'm trying to integrate that topic with other intriguing topics. So in addition to all those nice things Nanshu said already, and I'd like to add one more thing about the affection about the research topics. So,
Okay.
yeah, that's it.
Perfect. Thank you. And Wei?
I totally agree with what Nanshu and Miso said, and I think everyone has a big picture, at least which topic you want to work on. It could be energy, it could be healthcare. For me, I really like to work on medical technology for human health. But after you pick the big topic, actually regarding to research, how to pick your research project, how to pick your research specific topic, right? I think most importantly is understand what is the big problem right now. What is the real challenge right now in this field? What is missing right now? So where is the gap, basically? How can we tackle the problem and bridge the gap? So for me, my experience is talking with people. So when I meet, for example, if you want to work on healthcare, you cannot avoid talking with clinicians or like medical scientists. So when I'm talking with them, I realize that something what I originally want to do might not be that important because they have some real problem, what is actually challenging right now in their mind. So after discussion, actually, we found the right direction. So we think, for example, right now, what we are working on is a wearable, really chemical molecule sensing. We think that is right now the big gap, what is missing in the medical technology field. So after we pick the right topic, certainly which kind of disease, which kind of markers, that's also, we need in close interaction or discussion with clinicians. After we pick the topic, actually, what we can do as a professor is really assemble the right team, build your research group. So I'm very grateful for my all my current members right now. I think we pick the right people from different fields, how to work together collaboratively, and also super importantly, also Nanshu mentioned, I think working with others. No one knows everything, especially in such an interdisciplinary field, medical technology. Right? I think choose the right collaborator and work closely with them really save us a lot of effort, and we can actually make a big progress in this field. That's what I want to say.
Good.
Thank
Terrific.
you.
Thank you. So inspiration, going and gathering data from others, finding what it is that you love and gets you out of bed every morning, and then relying on your students and mentors for help. Those are all wonderful pieces of advice from our three rising stars. Let's go on to the current situation. What is it that you're trying? Is there some way that you're working with your groups or with others around the world where we have this long period where it's difficult to travel. Many of us can't go into the laboratory, or if we do, it's for only special circumstances or experiments. Maybe we'll go backwards this time, starting with Wei, and then Miso, and then Nanshu.
Current situation is pretty challenging because right now the school has been locked down for like several months. So we have to find a way to still work together and make good progress. And what we found is really there are several approaches. So firstly, some students they could dig a bit more fundamental problem, do the computation, simulation at home, and we still remain our group meeting, of course, virtually. So in this case, we can also track the progress of a student. Some student can write a paper, write a review, for example. And also, we found another important aspect we want to contribute because right now we face the humanity, the problem, the challenge of the humanity is really COVID-19, right? So we actually have a project that working on tackle the problem for COVID-19 management and tests. So we, because we are working on medical device field and we have multiple members working on this topic, we think we can make more contribution at this special time to this field, to our healthcare.
Okay, cool.
Very good. And Miso?
Yeah. The thing is, I'm in Korea, so we are kind of leading our normal routine, except that we have to wear masks all the time. Wearing the facial mask all the time, even in the meeting, so we are cautious, but we are trying to get back to the we're just leading our normal life. So I feel a little bit guilty to other people all over the world. My sister is staying in the United States. She's in lockdown for 1 month with her baby, and she cannot go to her school. But here it's the same. So we trying to keep the meetings virtually, so that we can get cautious, we can become cautious about everything, and then not to make worse things from the current situations. And this time I learned a lesson that we have to be more proactive to get connected with other people by emails, and then to ask for some like Zoom meetings like this. Otherwise, you can be really isolated from ideas. And then from this platforms, from this kind of platforms, we have more opportunities to learn something from other people, but it's not really interactive sufficiently. So the way to overcome these problems is you have to be proactive yourself, and then ask for interactions, like for even virtually all over the world, from your friends and from your colleagues, and that's what I'm trying to do. And I feel so sorry for other people all over the world, because I can work in my office right now. So
Well, that's a good
okay.
news. We know. Yeah.
Yeah, in Korea we are in a kind of relatively a good situation, so wearing masks is the only option.
And Nanshu?
Yes, so like Wei mentioned, some of our experimentalists started to show simulation talents, which is really surprising and encouraging. And also, I try to focus on polishing my students' writing skills, because they are usually so busy with coursework and lab work, and they don't have time. But now we have plenty of time to even read some writing advice articles or books. I hope they can appreciate how important writing is for scientists. We are ultimately writers, essentially. And also, it is a good time for us to brainstorm, just thinking wildly, looking into the future and into our vision. So I actually appreciate this time of break with both myself and also my students.
Okay, cool.
Those are all great activities. So take time for things that are difficult otherwise, thinking and connecting and writing and improving, and amplifying what Miso said. I actually took a class this quarter from one of the other iCANX speakers. Zhen Gu teaches a drug delivery class in bioengineering, and since I was home anyway, I thought it'd be great to learn what he had to say. And I could see there, as Miso said, it's a little more difficult to interact. And the students and in the class who had more to say and interacted more just obviously got so much more out of the class. So to the students and postdocs out there, by all means, speak up under these circumstances. We're waiting to hear from you when we teach or give a lecture. And it does take, as Miso said, it takes an extra effort, but it's better for you, it's better for the other students, and it's also better for the professors and lecturers or whoever it is you're interacting with. And it does take an extra effort, and it is awkward, to speak into the void, as we're each doing in our own homes or offices now. But, Alice, you've done an amazing job connecting us and connecting the world. And we so appreciate what you're doing here and what you do every week, and the phenomenal enthusiasm and vision that you had to put this together. And so I
Okay,
think,
thank you so much, Paul. Actually, I feel really great for this Rising Star talk. Today we achieved numbers really high, much higher than last week. So I think all these rising stars really attractive. Hi, Yuri, did you have any words to add efforts here for the young generations? How?
Well, I think we all have heard very good advices from our rising stars. And I agree with everything what has been said. And we have been doing in my lab a lot of the same things. My students got more time to analyze their results, dig deeper into the data, rather than go to the lab and make another experiment. And we found some interesting trends. We started a journal club in my group that weekly we discuss interesting paper from the field. And also I encourage my students and postdoc to listen to these numerous talks online, including, of course, iCANX-Talks. And actually, one of my postdocs, like 10 minutes ago, already sent me a comment on Nanshu's lecture, and he got an idea from the electrodes, how he can apply to his two-dimensional MXene antennas research.
Wow.
So I think it's really inspirational. It's really helpful. And I think even when pandemic is over and the world hopefully will go back to normal, whatever the new normal will be, we will still use a lot from the online communication, online presentation skills, practices that we have been developing during this difficult time.
Okay, it is great. Hi, Paul. Due to the time, I think we need to go to the next session. Yeah, so it's your time to announce for this second one.
Okay, shall I introduce or I?
Yeah, sure. Yeah.
Very good. Okay, so our third rising star is Wei Gao from Caltech. He was an undergraduate.
No. So,
Paul, I get
introducer.
Okay, that's what I was asking.
Yeah. Paul, sorry about that. You see that delay. So I want to announce for the second iCANX, ACX, Nano Rising Stars lectures. That's on the screen. Yeah.
Right.
So we'll be September 1st.
Yes.
Yeah. So
right.
you go
so
ahead.
our second set of Rising Star lectures